Now that we've learned how to do linear regression in R, let's look to see how we do multiple regression in R. It's very simple. It's a basic extension of the basic linear regression model. So recall that in an earlier video, we took a data set from the General Social Survey and we read it into R and we created a data frame. Let's look at the namespace of that data frame. So if we run this, and we look at our output window. So again, notice that there's a number of variables that we have to work with here. In this video, I'm going to focus on the following variables: education, father's education, age, sex, and race. And so let's go back to my script. Let's start by just reproducing the model that we created in the last video. Remember that in R, if we wanted to estimate a regression model, we use the LM command for linear model. And then we have to specify the model syntax. In this case, we're going to specify the simple regression, where education is a function of father's education. And then we can use an option to tell it which data it's coming from. And it's coming from the data object data set. It's a data frame. So I can run this and save it as model 1, a new object in R. And then I can just basically use the summary command on model 1. And then I can look at the output and interpret it. And so we see here basically that we have the formula we used, something about the residuals, which we will kind of ignore for the moment. We have the same results that we got in the last video. Basically, we have a slope effect for father's education, telling us that roughly for every year increase in father's education, we're predicting that the response education increases by about a third of a year. We have an intercept value of about 10, that's meaning that for those who have a father's education of 0, they're predicted to have 10 years of education. We have very low p-values. These are in scientific notation, meaning that this is 2 times 10 to the negative 16th. Both have 3 stars associated with them, meaning that they're significant at the 0.01 level. So these two are significant effects. We also have an R-square value that's equal to 0.2126. And so that tells us that about 21% of the variation in the dependent variable education is explained by this single independent variable, father's education. Okay, well that's nothing new compared to what we've already seen. But what if we try to do something a little bit more complex? What if we try to add yet another variable to our model? And so I'm going to make a new object called model2, in which I estimate another regression using the linear model command. And again, education is going to be my dependent variable. And my independent variables are going to be father's education, and in addition to that, I'm going to use the age of the respondent. So again, the tilde is the thing that's going to be used to differentiate between the dependent variable, which is going to be on the left side of the tilde, and the combination of independent variables, which are going to be to the right of the tilde. So here, age and father's education are both on the right side of the equation, and hence both are independent variables, and we'll have basically the additive effect of the two. And so here we're statistically controlling for age, and then looking to see what the effect of father's education is going to be. And again, I'm going to designate that the data are coming from the data frame dataset, another object that I created earlier. And so I'm going to run this, and I'm also going to run the summary command on model 2 to see how different the results look. So if we go to the output that's generated, again, we can kind of ignore the residuals for the moment. We see that we have a new value for father's education. Instead of being 0.33, now it's about 0.35 if we round it. So that effect has gone up a little bit, and that's because we've statistically controlled out the effect of age. So now we have the effect of father's education net of the effect of age. And then the effect of age looks like it's positive. And so you can see that basically for every year increase in age, we're predicting that the response education increases by about 0.2 of a year of education. So not very much at all. And then the intercept tells us basically what is the predicted value of the response education for somebody who has a father that's 0 years of age and whose age is also 0. Right? So that's kind of a nonsense result. We don't have anybody in our data set with 0 years of education. But nonetheless, that's how we interpret this value. It's about 9 years of education. And we can see that all 3 of these are significant at the 0.01 level. And this time, our R-square value, again, is about 0.22, indicating that collectively, age and father's education explain 22% of the variation in the respondent's education. All right, what if I wanted to add yet another complication to our model, make it even more sophisticated? So suppose that I didn't think that the effect of age was linear. Let's suppose I thought it was curvilinear. So let's say that I thought that at young ages, people got more education, but then at some point, the value starts to level off. And then people at older ages ended up having lower education because in the past, people got less education than people do in the present. So what I can do is I can add an age squared term in my model syntax. And that's really easy to incorporate. So I'm going to make another regression model. I'm going to save it as an object called model3. Again, I'm going to use the lm command to make a linear model. Education is going to be my dependent variable again. I'm going to have values of father's education and age. But in addition to the main effect of age, I'm also going to include an age squared effect. And I enter that with this I option, basically. So if I don't actually have to make a variable that's equal to the square of age, if I put in this I and then in parentheses the value that I'm trying to create, R will actually do that on the fly, which is very useful. And then again, I'm going to tell it which data set it's coming from. And it's coming from the data frame that I've called data set. And so I'm going to run the model, and I'm going to use the summary command to look at the results. And so if we kind of scroll down to my output window, we see now that we have a estimate for father's education, an estimate for the main effect of age, which is positive, and an estimate for the squared effect of age, which is negative. And so now we see that this has not changed that much. Again, we got a value of about 0.34. It's positive. That means for every year increase in father's education, response education is predicted to increase on average by about 0.3 years, about a third of a year, a little bit more than that. But now we could have to interpret the effect of age and age squared together. And since the main effect is positive, this is going to be an increasing function. So at low ages, basically, as a respondent gets older, they get more education. But because of the negative effect of age squared, which you'll see is much weaker than the main effect, eventually, as we get into higher values of age and this age squared term starts to kick in more and more and more, it's going to start to bend down the curve. And so in effect, what we have here is an inverted U-shaped function. And so what's going to happen is that for low values of age, education is going to increase, but it's going to increase up to a point, and then it's going to shift, and it's going to start decreasing. And so if we actually wanted to graph that effect, what we could do is we can install another package. And so if you install this package called margins using the install packages command, now I've already got it installed, so I won't actually do it, but you should do this. You can create a graph of the predicted probability of the age effect. And so we're going to bring in the margins command that I've already installed using the library function. And then we can use any command that's available in that margins library. And the command that we're going to use is margins. So the margins, what it basically does is it calculates something called an average marginal effect. Basically a kind of probability, predicted probability. It's going to calculate a predicted value or y-hat value for every value of the variable. And it's going to take the average of that. And so what I'm going to do is I'm going to run this margin command on the results of model 3, where I have both the age and age squared values together. And then I'm going to tell it that I'm going to estimate the average marginal effect for different values of age, ranging from 18 to 89 inclusive. And I'm going to do that as a list. And this at option basically tells me to calculate the average marginal effect for different values of age, starting from age 18 through age 89 inclusive. Now this takes a little bit of time to run. So we're just going to kind of let it run in the background. And as soon as it's done, we can look at the resulting output. And it's basically going to show us the predicted probability for each person, averaged for each age. And so it's finished. We can go down to our output window, and you can see that it has the different ages listed, and then it has the effect of age, which takes into account both age and age squared automatically, because both are included in the model syntax in model 3. So the other thing we can do is we can actually plot the resulting value, and so we can use another command called cplot to plot the values of model 3 after we run the margins command. We want to plot the value for age, and this what option basically just tells us that we can include some kind of a confidence interval, which again we'll talk about a little bit later in a future video. And I'm just going to include a title that shows that this is a plot of the predicted interval for age. And so if we run that, and then we just scroll out to the larger view, we can see that R has created a plot of the predicted probability of age, which you can see is curvilinear. You can see that at lower values of age, education's increasing up to a point. And the turning point looks to be about around the age of 60 or so. And then beyond that point, higher age is predicting less education. And then we have basically this gray shaded line, which is our predicted interval, which is a kind of confidence interval for the prediction to tell us where the true population curve is relative to the sample result. Okay, so that's pretty interesting. But now let's look at yet another set of models. Let's say that we wanted to include a nominal variable like sex. Well, in my data set, sex is actually a numerical variable. That might not be true for you. So in your case, it may be treated as a factor variable. And if that's the case, then you can just enter sex as another independent variable in your model. However, because mine is numeric, I'm going to have to specify that it's a factor. So I'm going to estimate a fourth model using the linear model command. And again, education is going to be my dependent variable. And following the tilde are my independent variables. Father's education, age squared. But this time I'm also going to include the effect of sex. And I'm going to include sex as a factor. Now what's the advantage of doing that? Well, normally you would have to make a set of dummy variables for each category of sex, except for one that you leave out as a reference category. If you treat it as a factor, R will actually do that for you automatically, so you don't have to actually do any recoding. And then finally, I have an option here telling us which data set the data are coming from. So I'm going to estimate this model and use the summary command on the new object that I create, model 4. And we're going to look at the output and see the new results. So again, I have some kind of an estimate for father's education. It doesn't seem like it changed a whole lot. I have an estimate for age and age squared. One is positive, the other is negative. Together, they make up an inverted U-shaped function, like we saw in the last example. But this time, we have these effects net of the effect of sex. And so this should be interpreted basically as the effect of the value of 2 for sex, which is going to be females. And the omitted category is 1, which is males. So this is the effect of females relative to males. And that's net of the effect of age and father's education. So we can see that we have a value of 0.23. So what does that mean? Well, that means that women, on average, have about 0.23 years of education more than men, net of their age and their father's education. And then this intercept here is going to be interpreted as the value of the response education when all of these values are set to 0. That is, for somebody who has a father's education of 0, whose age is 0, and whose value of sex is equal to 0, which is just males. Okay, and so we can see that all of these are statistically significant at the 0.01 level, except for this one. So sex actually is a non-significant effect. And we can see that the R-squared value is 0.2321, meaning that about 23% of the variation in education is accounted for by the combination of father's education, age, and sex. Okay, so now let's look at one more model. My final model, model 5, is going to add another nominal variable, race. Now, race is a multi-category variable. And again, normally we would have to make separate dummy variables, that is, variables that are coded 0 or 1 for race, and we'd have to include them as separate variables in the model. But if we treat them as a factor variable, R will automatically create a set of dummy variables and omit one of the categories as an omitted reference category. So I'm going to estimate a new linear model, or a multiple regression, in which education is the dependent variable, and my independent variables are father's education, age squared, and then sex. And then I'm going to have 2 different variables for race. I believe that the omitted reference category is going to be white, and that means that black and other are going to be ones that are included. And then I just tell it that the data are coming from the object data frame data set. So I'm going to run the model, save it as an object model 5, and then I'm going to run the summary on model 5 to look at the results. Okay, so if we scroll down to our output, here are the results of this regression. So here we have, again, an intercept telling us the value of the predicted value of the response education when everything in the equation is set to 0. That is, father's education 0, age is 0, sex is 0, that is males. And then these 2 race variables are also set to 0, meaning that this is for the reference category 1, which is whites. Everything else looks the same as it did. The difference here is that we have estimates for both the effect of race 2, which is black, and then race 3, which is other. And then by default, the omitted reference category is race 1, which is whites. So how do we interpret this? Well, we can say that for blacks, race 2, on average, they have 0.17 years of education more than whites, net of their father's education, age, and sex. And likewise, race 3, which is other, they have about 0.02 years of education more than whites on average, net of these other factors. However, these aren't statistically significant, so we can't know if this difference is different from 0 in the population. In effect, these are sort of non-effects. The only significant effects are the effects of father's education, age squared, and the intercept is significant. That means they're different from 0 in the population. Okay, so that's all fine and good, but what we could do is we could actually make some kind of a publication quality table to show these results. And so I'm going to do that using the Stargazer library. Now remember, I installed Stargazer in one of the earlier videos, and so I'm just going to bring in the library to make sure I can use the Stargazer command. And before I run this command, I'm going to create a vector for the variable labels, so for some of the variables in my model. And so again, a vector is created with the C function. And the things that I'm going to include as independent variables in my model in order are father's education, age squared, male, black, other race, and then also the intercept. So those are the things that I'm going to include as the contents of this vector. And now I'm going to create a publication quality table, or as near as publication quality as we can get without using something like LaTeX, using the Stargazer command that I can now use since I brought in the Stargazer library. And I'm going to include all the models that I estimated, Model 1, Model 2, Model 3, Model 4, Model 5. I'm going to make this a text file. I'm going to give it a title, Linear Regression Models for Education. I'm going to label my dependent variable as education. I'm not going to have any kind of a caption for my dependent variable, so I'm just going to leave that blank. I just use 2 quotation marks to indicate that there's no value there. I'm going to label my columns above each of the various models as Model 1, Model 2, Model 3, Model 4, Model 5. I'm not going to put model numbers. That is, it's not going to number them. Those numbers are already explicitly going to be shown in the model number. And then I'm going to label my independent variables or my covariates using these variable labels that I created up here. So this object will be passed as an argument to this option. I'm going to create a new file called table out. That's going to be basically a new actual physical file that's in my working directory that I can look at that will have these results, which will be a nice, much more cleaner looking kind of thing. And then I'm going to keep certain statistics, in this case the number of cases and the R squared, and I pass those as an argument using a vector. And then everything's going to have 2 digits. I'm going to use that with the digits option, and I'm going to have some stars cutoffs for my asterisks, like you saw in the table. 0.05 is going to have one star, 0.01 is going to have 2 stars, and 0.01 is going to have 3 stars. That's to indicate the level of statistical significance. I'm going to have the single row option set to true, and that basically means that everything is going to be in a single row rather than in multiple rows. And then I'm going to have basically a note that just says the source of the data. So if I run this, as long as I remember to run this as well, it's going to create my table. Now it's a little bit hard to see here if we look at our output window, but notice that we have basically all of the variables here. They're regression coefficients along with some stars. We have basically the standard error in parentheses. Below we have the number of observations. We have the R square value, and we have some notes down here. Now this doesn't look particularly good. One thing that we could do is sort of try to resize the window, and that will make it look a lot nicer. And then we can kind of just scroll through it. The other thing we can do is we can look at that physical file that's created as part of our output window. And so you can see that basically the effect of father's education changes a little bit. It goes from 0.33 to about 0.35 we control for everything. That's because in this earlier model, we weren't accounting for the unmeasured effect of things like age, sex, and race. And now we are. It looks like the age effect changes a lot from this model to this model because we account for the curvilinear effect, but then it kind of stays the same. Again, it's an inverted U-shaped function like we saw in the graph. The effect of male doesn't change very much from this model to this model. And then we can see that basically the effect of race is only in one model, so it doesn't really have any chance of changing. And then we have our intercept changing quite a lot because we basically, it's interpreted for different combinations of variables that are set to 0. One thing that we kind of should pay attention to is the sample sizes are a little bit different across these things. Really, we should try to standardize them by using something like listwise deletion. But most of them are pretty consistent. And then you can see that the model fit is still kind of low. We're explaining only about 22-23% of the variation in education with respondents' education. But nonetheless, there's a number of other factors we still could account for that we don't account for, that we could make this model even better. So basically, that's how you estimate regression models using R.